Okay, so this is question 2 from the 2024 Step 2 paper. Honestly, I think this is the most straightforward question out of all 12 of the questions. But you do have to be careful because it's kind of easy to make a mistake here. And I say that because there's like a lot of computation in this question. So if you do any like calculation mistakes, then yeah, it's easy to do a calculation mistake, basically. What I'm trying to say. Anyway, let's just go into the first part. So they ask us to find the binomial, a series expansion of 8 plus x cubed to the minus 1. And if we just remember what the formula is for that, it's looks like something like this, right? And it's an infinite series. And if we remember that it needs to be a 1, right? In the term. So we need to factor out 1 over 8, get this formula to work. So once we do that, we should be able to just plug in the numbers or plug in the terms. So x cubed over 8, plug that in for x, or the x term here, and for each of them. And then the n term, or the n value, which is going to be minus 1, and you should get something like this. And so if we look at what they want us to show next, or hence show next, we turn an integral into a sum, right? So it's probably a good idea to turn this or show this binomial expansion as a discrete sum. So once you convert it into this, you get something like that, and that should be the answer to the first uh, first line. And then for the hence show that, we have an integral, and that turns into a sum, right? And we only have this information. They've only told us to convert this into the binomial series expansion. And we have it in this integral, right? So the the first thing to do is just to just substitute our sum into there. We get something like this, right? And so now we need to think about, oh, okay, how do we get to what they want? Where they just only have a discrete sum here. Well, we need to get rid of the integral somehow, right? And it's a what's it called? A definite integral. Yeah. So an idea could be to, well, what if we could somehow evaluate the definite integral, right? But the problem is that we have this discrete sum here, which is kind of annoying because we don't know how to deal with that within an integral. So what would really be nice if we were able to sort of like swap the places of the discrete sum and the continuous sum, which is the integral. And if you just test that out, right, and then just follow through with trying to simplify that, you actually end up with this answer, right? So that could be one method of trying to do it. Also, they say here you don't need to consider issues of convergence, right? And if we don't need to consider issues of convergence, an interesting thing to know is that you can actually swap these the discrete sum and the continuous sum, right? So that's just something you need to know. But you can sort of like intuitively guess that that might be the case since they both represent sums, right? Just one is continuous and one is discrete. And even if you didn't know whether it was true or not that you can swap them, you can just try it out, right? Like just swap them and see what happens from there. So when you do that, you should get something like this. And then we're only integrating with respect to x, right? So we can take out um, any of the other factors or terms that don't have an x in them. You get something like this, right? And yeah, so we're nearly there, right? We're almost at what they want. We have this term. We just need to get this term, right? And we have something like this. So let's just evaluate this inside integral. And when you do, you get, well, you get what they want. So they ask us to show that this is equal to that, and they want us to evaluate this. Well, if you look at this, it's actually simple to evaluate. It's just ln, right? Oh, or the log function. But how do we get this into an integral, right? Well, they've shown us that this is equal to an integral, right? So if you look at this, you can actually just expand out the terms, right? So this will be three separate sums uh, in the form of this, right? Where if you just look at this one, the only difference is plus 2, right? So if you say m is equal to 2, then it's basically the same as this integral where m is equal to 2, right? And so if you do that for each of them, you should get something like this, where yeah, m is 2 here, m is 1, and then m is 0 here. And then those will convert to their respective integrals. And we're adding them all up, right? So we get something like this. And now we need to somehow simplify it to this, right? Yeah, you can do it any way you want to, but I think the easiest and the quickest way is just to just know the sum of two cubes, like the factorization for the sum of two cubes, which factorizes into what we have in the denominator, and that like just perfectly cancels out with what we have on top. So that's kind of nice. And when we get this, we just need to evaluate this integral, which is not too bad. That gives us this. Uh, yep. The next part we have, oh yeah, show that this is equal to this. So we just need to use the same idea as we did before, right? We need to get this into the form of this, right? And we see that we have, if we did expand the bottom or the denominator out, we would get a, a quadratic, right? In terms of k, and we have a linear term on the top. So we just need to like do turn these into partial fractions, right? Because then we would get terms which are in this form, right? Where we just have a linear term on the bottom. So when we do that, it's kind of a long process, but we should get a is equal to 24 and b is equal to 24. And so then when we convert those into integral form, we get something like this, right? Because m is 1 here and m is 0 there. We get something like this. And then from here on, it's just however you want to integrate this function, right? I think the most straightforward way is to just do partial fractions again after you factorize the bottom out, right? Because we already know from before that we can factorize it with the sum of two cubes. And then when we do partial fractions again, yeah, this was what I was meaning by it's kind of easy to make a mistake. There's like a lot of computation. But when you do it again, you should get a is equal to -2, b is equal to 2, and then c is equal to 16. And when you do that, you get something like this, right? And we know how to integrate this, right? Because, I mean, we had a similar integral before. It's just ln. And then we have something like this, which it would be nice if, well, it's almost what's it called? A log as well, right? Like a reverse chain rule. Because this bottom one would integrate or would differentiate to 2x minus 2, right? But what we can do is we can just do in the numerator, we can do -2 and then +2, right? Because that would have no effect. I mean, the overall sum of that is 0. And then we would be able to do the reverse chain rule on the denominator easily. So something like this, right? But because we minus by 2, on the top we need to add by 2, so we get an 18 there. And that one, you have to use the arctan integral, right? Because we have a quadratic on the bottom and then a linear sum on top, so that's in the form of arctan after you complete the square, right, on the bottom. But once you evaluate the integrals for all three of them, you should get something like this, and then you just need to add them all up, right? So this this minus ln4 will cancel out with plus 2 ln2, and then we have ln3 minus 2 ln3, so we should get minus ln3, and then the other term is pi root 3, right? We get pi root 3 minus ln3, and that should be in the form of what they wanted, right? So yeah, so a is just 3, and b is 3 as well. Yep, and that's the whole question.